If you're looking for an easy way to visualize audio tracks, you've come to the right place. We are going to create an inheritance model that will empower you to facilitate a simple engine for generating audio values. All of your inheriting classes will be given the power to manipulate objects according to the audio track that is currently playing. However you decide to manipulate objects will be left to your own creativity. But here you're going to be given an example of how you might scale objects given a certain audio track. Okay, so this system is really only comprised of two major scripts. We have AudioSpectrum, which is going to be our engine, and then we have AudioSyncer, which is going to be our parent class through which all of our visuals are triggered. The other scripts are derivatives, and will wait for instruction from AudioSyncer. We will only be going over AudioSync scale in this tutorial. So first, let's go ahead and see what our main engine AudioSpectrum is going to need. Create the script and open it up. The first thing you'll need to do is define some class members. For our engine, we need an array of floats to hold our spectrum data. This spectrum data can be used to serve music beats in any way that you wish. We will be using a very simple method of extracting beats from this data. Secondly, we need a publicly accessible value that can be accessed from anyone who needs it. This value is going to be highly generalized from the spectrum data array. In our start function, we should initialize our spectrum data as an array of power of 2 size. That is, our array can be size 32, 64, 128, 256, so on and so forth. I found that a size of 128 works just fine. Now in update, we need to populate the spectrum array. We'll do this by pulling data from our scene's audio listener. Call this method referenced from Unity documentation to fill your spectrum array. Now, at this point, many people run complicated analysis algorithms on the spectrum data to ultimately extract beats from music. However, we are simply going to check if our spectrum data has anything in it. And if it does, we will assign our generalized spectrum value to the first element in the array of data, and then multiply it by 100. Now, 100 is an arbitrary value, and I'm only using that to denormalize. You could use any value here that you want, or you could choose not to multiply it by anything at all. Now when you're done, the AudioSpectrum class should look like this. For more information on spectrum data and how Unity gets it, check out these resources linked in the description about the GetSpectrumData method and the FFTWindow enumeration. Okay, so next we want to create and open the AudioSyncer script. As a reminder, this script is the parent class for all different types of syncing manipulation. For instance, if we want to scale objects based on sound, we create a script for that. And if we want to change the color based on sound, we would create another script for that. And all of these scripts will derive from the one that we're about to create right now. So first, we want to define a couple of variables. We will have bias, which determines what spectrum value is going to trigger a beat. Time step, which determines the minimum interval between each beat. Time to beat, which determines how much time before the visualization completes. For instance, if we go from scale of 1 to 2 on a beat, how long does it take the object to do that? Then we'll have rest smooth time, which determines how fast the object goes to rest after a beat. To continue the example, how fast does the object go from a scale of 2 to a scale of 1 after a beat? Then we'll have previous audio value and audio value, so that we can determine if the value went above or below the bias during the current frame, thus triggering a beat. A timer variable to keep track of the time step interval. And finally, a boolean to keep track of whether or not the sync object is currently in a beat state. Now let's consider the functions of our script. We're going to use Unity's update function to hold our virtual onUpdate function. This is because we might want subclasses to inject their own update code without completely overriding the base class update code. In onUpdate, we assign the previous and current audio values based on AudioSpectrum.SpectrumValue. Now, if our audio value went below the bias in the current frame, we check if we are allowed to trigger a beat based on our time step rule, and then we trigger OnBeat. We do the same thing if the audio value went above the bias in the current frame. Finally, we must remember to increment the time step timer. In our onBeat function, we create a debug statement that will notify us when a beat occurs. Then we set the time step timer to 0 and flag the beat boolean to true. Notice our onBeat and onUpdate functions are virtual, so this implies all subclasses may need to do something with those functions as well. Let's create a subclass to control the scale of objects based on soundtracks to demonstrate how that's going to work. The first thing we want to do with the AudioSync scale class is derive AudioSyncer, the class that we just created. Now let's create some class members. We only need 2 vector3s to hold our scale values, one for onBeat and one for rest. When a beat occurs, we move to beat scale. Otherwise, we move to rest scale. The first thing I like to do in subclasses is override all virtual parent functions. So create an override method for onUpdate and onBeat. Remember, onUpdate is called in Unity's update function thanks to our parent class. In onBeat, we will spawn a coroutine to go to the beat scale. We're going to cover this coroutine shortly. In onUpdate, we will check if we are currently in a beat state, which just means that the scale is currently being manipulated by a beat. If we are not in a beat state, then we're just going to lerp our scale towards the rest scale. Now let's talk about the coroutine to get our scale to the beat scale. First, we mark our current scale and our initial scale. Then we create a timer to keep track of how far we are between the initial and target scale. While the current scale is not equal to the target scale, we go ahead and lerp toward the target scale. Then we increment our timer and assign the transform scale to the current scale variable. When our timer is equal to time to beat, we know that the current scale is equal to beat scale based on the properties of lerp. If any of this is confusing, I suggest learning about lerping and coroutines, but since that's beyond the topic of this tutorial, I'm going to go ahead and move on. After we reach the target scale, we set isBeat to false, notifying the class to continue lerping towards the rest scale. Check the contents of your script with mine, and then let's go back to the Unity editor to see how all of this works. So from an empty scene, what we want to do first is create an empty game object. This is going to be our audio. We'll go ahead and add a component for audio source. So audio source, and then from here you would want to drag in whatever audio clip that you have. Now I'm going to add audio spectrum, which remember that is like our little mini engine for generating beats. Now at this point, I want to create the object that's going to be manipulated by my audio so that we can actually visualize that working. So I just created an image and I set that to be the center point of my screen. And I'm going to add the audio sync scale component. So we'll go through all of these values one more time really quickly. Bias is the value that dictates when a beat is triggered based on our spectrum value. So what that means is if I say this is 25, then whenever my spectrum value goes above or below 25, a beat gets registered. Now that could happen really quickly. So what I do is I create a time step value, which we'll say is 0.15, which means that there can never be a beat, there can never be 2 beats that happen together in less than 0.15 seconds. That is the minimum interval. Then what we'll define is a time to beat. So how long does it take to get to the target scale, in other words? And I'll say that happens pretty quickly. So in 0.05 seconds, we will reach our target scale. Then how fast do we go down to the rest scale? And I'll set that to a value of 2. And this isn't in seconds, this is just a speed variable. So the higher this value is, the faster we will reach our rest scale. Now I just defined the beat scale and the rest scale. So I'll say whenever we get a beat, I want to see the square go up to a scale of 2. And then when we are resting, so when there is no beat, my scale should be 1. And then I'll go ahead and play this. Okay, so that looks like it's working pretty well. Now you'll notice that whenever the song is playing, there's moments where nothing is happening. And so what we can do is bring our bias down, which just means that the spectrum value can be lower before a beat is triggered. So if we set this to 5, we're going to see a lot of motion on our square. And then I'll go even lower from 5 down to 1, and it should be almost always moving up and down. So what we can do with this is create different UI elements on our canvas that represent different biases or different spectrum values. And after moving our elements around in the orientation that we want them to be in, we can end up with something that looks like this.